For section 7.5, we're looking at more trig equations. We're going to use a few different techniques in this section that we did not do in the last one. We're going to use identities. We can always plug in an identity. Basically, we're doing a substitution here. Think of it as if when you used to do two equations with two unknowns, and you would have like an x plus a y equals something, and then you'd have 2x minus 4y, something like that. And you'd substitute for x or y in one of the equations. Similar idea here, except I'm not told the second equation, but remember, I have a whole sheet of identities that I can use. And now there's usually more than one way to go about this. So you might see a different method than I use. But on number one, what I'm going to do is I'm going to replace cosine squared with 1 minus sine squared. So I'm using that variation of the Pythagorean identity. And so I'd have 2 minus 2 sine squared on the right side. And if I group everything over to one side, I'd have 2 sine squared. I'd have plus a sine. And then minus 1. So I had a 2 on the right, and when I subtract it over, I'm left with minus 1. And now it looks like a quadratic style problem. That I can do some factoring, hopefully. So again, think of it like 2x squared plus x minus 1, except it's going to be 2 sine theta. And then let's see, that's going to be 2 sine theta minus 1, sine theta plus 1 equals 0. So if sine theta equals a half, we're covered. Or if sine theta equals -1, we're covered. So we go around the unit circle and figure out where sine equals a half. We've already done this. That happens at pi over 6. And at 5 pi over 6. Remember, the plus those are both those answers plus 2k pi. Where does sine equal -1 on the unit circle? That only happens at 3 pi over 2. And then I have plus 2k pi on that. On letter B, I've got sine 2 theta. Okay, so double angle. I'm going to replace sine 2 theta. Again, I'm using an identity here with 2 sine cosine. Now, it might be tempting to divide cosine out on both sides, but I could have that cosine equals 0. So if I'm dividing out 0, I can't divide by 0. So instead of dividing it out, I'm going to subtract this cosine over. And factor it instead of dividing it. So I achieve basically the same thing as dividing it out, but I don't risk that division by 0. So in this one, if cosine equals 0, we're covered. Or if sine equals a half, we're covered. So for the sine equals a half, I'm not going to rewrite it. That's the same answers. Oops. The same answers that we had over here, pi over 6 and 5 pi over 6. Where does cosine equals 0 going around the unit circle? That happens at pi over 2 and at 3 pi over 2. And again, both those answers are plus 2k pi. So every answer is plus 2k pi. So I have pi over 2, 3 pi over 2, pi over 6, 5 pi over 6. For letter C, I've got another double angle here, cosine 2 theta. Now remember, cosine double angle had 3 different options. You can pick any of the 3 options, just one may take a little longer than the other. The fastest one that I saw, and again, remember on these, there's usually more than one way to do this. The fastest one I saw was to replace it with the double angle 2 cosine squared minus 1. And again, any one of these would work. It just might take more time. This was the fastest one I saw. So I'm going to replace it with 2 cosine squared of theta minus 1. On the other side, I still have cosine squared minus a half. If I group the cosine squareds together, if I subtracted off a cosine squared, 2 of those minus 1 is going to leave me with 1 cosine squared. If I add this one over to the other side, I've got cosine squared equals a half. Square root both sides. I don't have to do any factoring on this one. If I square root both sides, I have that cosine theta equals plus or minus, be careful here, square root of a half, well, the square root of 1 is 1 over the square root of 2, but that rationalizes into plus or minus root 2 over 2. And those are numbers that we know. So it's saying, all right, where is the cosine equal to positive or negative root 2 over 2? Well, that happens at every 45. So pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. And again, all of those answers are plus 2k pi. For our last 2 problems, we have the multiple of an angle. Now, technically here, yeah, that's a double angle. You could use tangent's double angle identity, but I'm going to show you a faster way to do it. So what we're going to do is we're going to sub in for the angle. So 3 theta particularly, we don't know what that is. That's not a double angle, that's a triple angle. So on these ones that involve the multiple of an angle, but it's not convenient to use a double angle identity or something like that, I'm going to replace the 3 theta with the letter u, and that's just arbitrarily chosen. So instead of this being 3 theta, think of it as just a big letter u. That could have been a y or an x or anything, but typically they call it u substitution. So we're going to use the letter u. So now if I solve this for u, this is just getting sine by itself. So I would add 1, divide by 2. And so I'd have sine of u is a half. Okay, now this asks me, where does sine equal a half? We've done this a couple times already. This happens at pi over 6. And I'm going to write this out, and there's a reason why I'm writing it next to each one. It happens at pi over 6, and it happens at 5 pi over 6. Oops, over 6. Rewrite that. 2k pi. Now that is what u equaled. So technically it was u equals that. U equals that. But u is actually 3 theta. So I haven't solved yet for theta. I solved for a different variable. So what I have to do here to solve for theta is divide by 3. And that means I'm dividing both of these by 3. This is why I wrote these out separately. So I have that theta equals pi over 18 plus 2k pi over 3. And over on the other side, if I divide by 3, I get that theta equals 5 pi over 18 plus 2k pi over 3. Now, these problems also don't ask for just the general, give me all the solutions. It also wants all the answers between 0 and 2 pi. So think of these two as being like recipes. They're recipes that I then throw in k equals 1, 2, 3, blah, 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 and keep getting answers out. So the first answer I would be getting would be if I plugged in 0 for k. So in both of these, in the green and the orange, if I plugged in 0 for k, well, on the green side, that would just get rid of the 2k pi over 3. So pi over 18 is an actual answer. What I'm going to keep doing is hopping back and forth. So now I'm going to go to the orange one. If I plugged in 0 for k, you'd just be left with 5 pi over 18. Okay, now I'm going to turn it up to k equals 1. Back to the green side. If I plugged in k equals 1, I'd have pi over 18 plus 2 pi over 3. If you get common denominators, that's, what's that going to be? 8 over, or no, sorry, 12 over 18. 2 pi over 3 is 12 over 18. So that's going to be 1/18 plus 12/18. 13 pi over 18 is my next answer. Hop back over to the orange. Plug 1 into there. You're going to have 5 pi over 18 plus 2/3 or 12/18. That's going to give me an answer of 17 pi over 18. Go back to the green side. If I crank up k to 2, on the green side, that's going to give me pi over 18 plus, I would have 4 pi over 3, which is going to give me 24 pi over 18. So that would be 25 pi over 18. Go back to the orange side, plugging in 2 for k. I'd have 5 pi over 18 plus 4 over 3, which again is 24 over 18. That'll give me 29 pi over 18. So if I just keep going back and forth, increasing k by 1 each time. Now, if I took k to 3, that's going to make this 6 over 3 or 2 pi. So if you think about it, if that's already 2 pi, adding something onto it is definitely going to be above my limit. So you basically just keep going back and forth, adding, increasing k values until you reach the limit. So there's all the answers for theta between 0 and 2 pi. And again, we could have thought of every single problem that we've been doing with this solving equation stuff as this is giving me a general recipe for answers. And then I can start getting answers from that. All right, on the last one, again, I'm going to think of the variable. Let's get some stuff out of the way here. Sorry, not the variable, but the 2 theta, the multiple of an angle, as the letter u. And again, that's an arbitrary pick. But think of 2 theta as the letter u. And so to get tangent by itself, I would just multiply by the reciprocal of -1/√3, which would be -√3. So if I multiply both sides by -√3, I've got tangent of u equals -√3. So it canceled out on that side. Now remember, with tangent, you only have to find the answers between 0 and pi to start off with, for your recipe at least. Remember, for tangent, remember, we find all the answers in one period. So where does tangent equal -√3? Well, let's go back to unit circle stuff. Tangent, if I'm only looking between 0 and pi, tangent's negative in the second quadrant, and it would be a 60-degree reference that has a tangent of √3. Because if you did √3/2 over 1/2, you'd end up with √3. So what does that tell me? That tells me the angle is, that's 2 pi over 3 plus k pi, because remember, for tangent, the period is only 1 pi. But again, we just solved for the letter u, but u was 2 theta. So to get theta by itself, I have to divide everybody by 2. So that's going to give me theta equals, let's see, that's going to be pi over 3 plus k pi over 2. So just like before, I now have a recipe for answers. Fortunately, it's just a single recipe this time instead of 2 recipes. But I'm just going to start with k as 0 and keep increasing until I pass the 2 pi threshold. So pi over 3 is definitely an answer. If I make k equals 1, that would be pi over 3 plus pi over 2. If you get common denominators, add those together, you're going to get 5 pi over 6. If I crank k up to a 2, I'd really have pi over 3 plus pi, which is 4 pi over 3. If I crank k up to 3, you get common denominators, add those together, you get 11 pi over 6. And if I brought k up to a 4, well, that's already 2 pi. If I add something to it, it's going to be too much. So there are all my answers.